we going?
Yes, sir.
So, people at home, I just passed these out and around to everyone. They're models. And they're models of nucleotides. So we're talking about nucleotides here. So each nucleotide has a sugar, a phosphate, and a nitrogen base. Now the nitrogen base, if you notice, is a variable structure. It can be 4 different things, actually 5 different things. DNA has 4 different nitrogen bases: guanine, cytosine, adenine, and thymine. You should have a G, an A, a T, or a C. Now the guanine, if you notice, and the adenine, if you happen to have either of those, you can see they're double-ringed structures. They consist of 2 parts, basically. Whereas the thymine and the cytosine, C and T, are shorter. They're not as long. They're smaller. They're a single-ringed nitrogen base. And why do we call them nitrogen bases? It doesn't show it very well in your magnets, but it shows it well right here in your book. That's a double-ringed nitrogen base. So it's either G or A. And as you can see, there's nitrogens within the rings. You see those nitrogen atoms? They're real small. I should somehow make this bigger. But here it shows the nitrogen bases. There's G, there's A, there's C, there's T, and there's U, uracil. RNA has uracil instead of thymine as a base. Do y'all remember any of this from regular bio?
I do.
Yes.
God.
You do not?
Oh.
David, no? No memory?
Hold on, please.
They was just, maybe I'm close
So what we do is we take these nucleotides. Oh, and by the way, we call the G and A nucleotides, the bigger ones, we call them purines. You know how I remembered that in college? Oh. People from Georgia are pure. People from Georgia are pure. G and A are the purine nucleotides. And what's so special about the purine nucleotides? They're bigger. They're double-ringed. Georgia's a big state, I would remember. C and T are known as pyrimidines. And I would think people from Connecticut are pyromaniacs.
I like that one.
Yeah.
And they're little.
Didn't make much sense, but it went with the same theme. Georgia are pure, Connecticut are pyromaniac.
And Connecticut's small.
And Connecticut's a smaller state than Georgia. Bam.
Boom.
So, the single rings are your pyrimidines, double rings are your purines. And what will happen is, these will bond together on one side of your DNA molecule. Let's take a look at the DNA molecule. There it is. Beautiful molecule. On the other side, you will get, everywhere where there's a C, a G will bond to it. Everywhere where there's a T, an A will bond to it. G bonds with C. Guess what bonds with this A?
T.
T. Guess what bonds with this G?
C.
C. Guess what bonds with that T?
A.
Oh, y'all are good. And finally, what bonds with this G?
C.
C. I used to remember grilled cheese because in college I ate grilled cheese sandwiches all the time. They're actually microwave cheese sandwiches. I didn't actually grill them, but I still called them grilled cheese sandwiches. And I used to have a buddy of mine who liked them even more than I did, and I called him GC for grilled cheese. Anyway,
that counts, you know?
it was a strange college experience. But check this out. We have two sides to the DNA ladder. Now here's the thing I was talking about with the 5' and 3', the primes. Do you remember the phosphate is on the 5' end?
Yeah.
Okay, so this side of the DNA molecule runs 5' to 3'.
So
the phosphate is the 5' end, and down here on the other end is the 3' end. So this side runs in what we call in the 5' to 3' direction. That means on each nucleotide, the phosphate's on the top. This side right here runs in the 3' to 5' direction. The phosphate is on the bottom of each nucleotide. And there's always a phosphate sticking out on one end if you cut the thing off somewhere. The end that the phosphate is sticking out is the 5' end. 5' phosphate.
can it change from left, like, is it always that side's on the left and that?
All you got to do is flip the thing upside down and it'll switch.
Yeah, so like
Yeah.
you just.
So it depends on, so the reason, because since this is a 3D molecule that can be moved around, scientists can't refer to it as up and down.
Yeah.
They have to refer to 5' to 3' or 3' to 5'.
Gotcha.
So we say that the DNA molecule is what we call anti-parallel. This is parallel. This is anti-parallel.
Gotcha.
See what I'm saying? Parallel, anti-parallel. This could be my TikTok dance.
Okay.
A million hits.
Can we make
$100,000. Okay, so one more thing. The RNA, which are the green nucleotides here, they don't usually make double-stranded like DNA does. Usually they're just single-stranded. And Dylan, this brings up your point about the mutation. An RNA strand can mutate very easily. If you knock that out and these two rejoin, you've changed the thing. Or if that gets knocked out, another one can come in and it can be a totally different one. An A gets knocked out, a C can take its place. But on DNA, if a C gets knocked out right there, only a C can fit back in and take its place.
Yes.
DNA does not mutate very often because there's an opposite strand that only one thing can fit to.
Wait, I have a question.
Yes.
Is that why some viruses can mutate easily because they have RNA, not DNA?
RNA viruses mutate easily. DNA viruses rarely mutate.
Wow.
Chickenpox is a DNA virus. You get a vaccine for it when you're a kid, you'll never get sick from it again. It hardly ever mutates.
Cool.
The cold is an RNA virus. It mutates all the time. We can't come up with a good vaccine for it because it mutates so much.
Oh, so is that why there's so many strains?
There's no cure for the common cold.
That's right. Is that what?
Is that why there's so many strains?
That's
There's so many strands out there because they've mutated so many times. Now this coronavirus is an RNA virus. So it'll mutate a lot of times. What we got to do is we got to come up with vaccines before it mutates too much. That's why we're in a hurry here. If we can get it, if we wait for 10 years and it's mutated a bunch of times, you won't be able to come up with enough vaccines.
Gotcha.
Kind of an interesting problem, isn't it? Also notice this. A purine has to bond with a pyrimidine to make the DNA the right width. If you had a purine bonded to another purine, which is also big, look, it's too wide.
I see that.
And if you had a pyrimidine like T bonded to another pyrimidine like C, look, it's too narrow. You always have to have a purine and a pyrimidine bonded together. That's why G and C and A and T are how it bonds together in the middle. Now I want you to notice something. This is the last thing. G and C are more strongly bonded than A and T. there are 3 hydrogen bonds. Those are the dotted lines here, holding together the G and C nucleotides in the middle of the strand. There are only 2 hydrogen bonds holding together the A and the T. So G and C are tightly bonded. A and T are a little bit loose.
Does that cause, like, is that more mutations that happen in the A and the T area?
Maybe, but really why we're interested in it is sometimes you're going to have to unzip the DNA strand to copy it. The unzipping usually occurs in areas where there's a lot of A's and T's. That's how we know where to unzip the DNA to start copying it.
Got it.
Questions?
So, if you have a long strand of RNA, does it ever form these bonds with itself holding?
It
like
can.
protein?
It can. There are usually proteins that help it do that, and those are called microRNAs, and it's part of regulation, which we're going to get to about chapter 14 or so. No, less than that. Okay, that's it. I need my wipers to